which begins from 0 and ends at and is equal to 0. Start this. It is from the K, E, otherwise if I have such kind of two series, then their product is going to be a series in which each of this representative is a partial sum. So it's going to be the series of partial sums. Now, why this should be the case? Does it make sense? Does it make sense? So it should agree with our intuition. Should agree with our intuition. Our intuitive idea. Take A1 and multiply with everything. Multiply with everything and so on and so forth. Does it meet with our intuition? What will be seen on? What will be seen on? Let's see that why this should be true.
C dot is a series A naught B naught.
Just simply A naught B naught. C naught is A naught B naught. Okay. Listen. So roughly it is a product of these. And C1 is what? A naught B1 plus A1 B1. What I'm saying that okay, take this A naught and multiply with B1, and then take this A1 and multiply with B2 and put them in a one single coefficient. How about C2? A naught B1 plus A1 B1 plus
A naught B2.
or B. Okay. So give me any term you want from this product, and I'll tell you that it can appear in which of the C's actually. So you can see that by this manner, defining C's in this manner, you can cover all them. So in other words, you can have all these products happening. So take A1 and multiply with everything, and take, A1 and multiply with everything, and so on and so forth. So what we are saying that you will have this long series, okay? But we can put this long series, which is kind of jumble, doesn't make sense, in a sensible way, which is slightly weird. And none of the term is going to be this. Okay. Okay. Yes. You have to be very careful if you are multiplying. And this is going to be important, especially. There are going to be many instances when you have to multiply two series. You're going to see this in differential equation. You're going to see this in differential equation. You have one solution of differential equation. Compute another. Multiply two series here. So whenever and wherever, okay, no matter what subject that is, if you have a series, you should ask, or the legitimate question that should be asked is that this series convergent. If that series is convergent, trust the results. If the series is not convergent, what trust the result. For example, you people do lots of PDs, okay, and you have lots of crazy methods, series solutions. It's like they assume that okay, I have a very non-linear differential equation, and I want to. So I assume that basically the solution of non-linear differential equation is a series. So you take that series with unknown coefficients and substitute in equations, and try to compute the constant factor. You can try to make sense of the series. Now, like one of the major critique of serious mathematicians of this kind of approach is that how do you know that this series converges that you are assuming as a solution? Convergence is a bit problem. There are lots of methods which we use, which physicists use all the time. They say if we don't care whether it converges or not, it works, so it's fine. You cannot like that. You have to ask this question. If you have a series, then not. So it's like you are having a series, okay, and you want to know, or you are defining something in the terms of series. The first question that we all should ask is that whether it converges. For example, you say that e to the x is 1 plus x square over 1. X plus x square over factorial 2 plus factorial and so on and so forth. Some people write it bluntly that this is equal to this side. So your first response should be what on such kind of mistake? Don't forget about this. You're going to see that whether this is equal to this or not. The first thing is this convergent actually? Is this convergent? If it is convergent, then you can give it some meaning. So maybe that meaning is equal to the x or something else. But the first question is it convergent? You should always ask this question. Is it convergent? If you are having a series, so you are doing a Fourier series. Have you done Fourier series?
Yes.
You do it. So it's like you try to approximate your given crazy function with certain trigonometric series. Question: is that trigonometric series convergent? That is indeed. We always ask. So learning behind series is there is a purpose. You're not learning it for no reason. You're learning it for very concrete reason. That lots of mathematics is being done in the terms of series. You need to be very careful about this.
ये जो previously आपने example का e to the x ये जो होता है ना कि किस x की वैल्यू के लिए वो convergent है वो
Convergence for all. Basically, the convergence of this comes from the convergence of Taylor series. Taylor series is nothing less than Taylor series. I'll give from there. Okay. Anyway, so my central point is this: that whenever and wherever you learn something about series, that you define something in the terms of series, then you should always have the first question. Mind that if this series if it is convergent, then you can go ahead. But if you are defining something in the terms of something super, it doesn't make any sense. Anyways, okay. So with this definition, you can ask immediately the next question. That if this series is convergent, and this series is convergent, it is necessary that the vector product should also be. Okay? Answer is it is not necessary. It should also be. Okay? Can we say that if this series converges to A and this series converges to B, is it necessary that this product series, this new series, which is we have defined as a product of these two series, is going to converge to the limits of this and this? Not in general, but under certain assumptions we will have us in a series.
Sir, can't we check term by term multiplication? For example, taking A naught and multiply then we have scalar.
So you have basically then a trouble actually. The trouble is when just think about it. So you have an infinite number of infinite series. Because for every number, A naught you're going to have infinite series. You're going to have infinite number of it, which is going to complicate it actually. So that's a very clever way to define the product in the terms of just one series actually. Think about it. And none of the term is going to be missing from that. Will it make sense? That's a very good and clever way to define it. Okay. Here the this example given, I'm not getting into technical details. We are not getting into calculations. I'll just give you a. Imagine you take this. So you can ask a question that if this is A and this is B, then is it necessary that this product that you have
A and B.
is a B? Is it true? And I'll show you that this is not the case necessarily. Take something very simple. Take this series. Minus 1 raised to n over n. Scale of n. But you can ask obviously the same question about this series as well. So I have something very crazy. Anyway, so we have this. So what I'm doing that I'm saying that imagine I would like to consider the product of this series with itself. Forget about something.
A and B are same as A and B are same.
Forget about something different. Let's see that whether it makes sense. One multiply. Obviously, this is going to be Cn. This is convergent. This convergent. Just think about it. Converges to what?
Yes, sir. P is very 1.2.
First of all, I can apply alternating series test, or I can apply every test here. This has bounded.
Decreasing.
Decreasing sequence. And if you take limit and to infinity,
It goes to 1.
P series 1.
you need to be careful. Theorem 3.43, it says that by 3.43 convergence. Theorem 3.43. Okay. If I'll pull out scale of n, I'll take limits. In other words, why this guy is going to get to 0? Is this guy going to get to 0? Yes, this is going to get to 0. There's no need to rational, just pull out and it's fire outside.
0.66.
Okay. This goes to 0. So in other words, it satisfies the condition of being a replacement. So it satisfies the conditions of every test. This should converge. Okay. So how many of people understood that why this series is convergent? Okay, good. So I like to think about my CN actually. So what would be CNR? So it is going to be. It is going to be. It is going to do one. So I'm just writing the series directly. 1 over square root of 2 plus 1 over square root of 2 plus 1 over square root of 3 plus 1 over 2 square root of 2 or square root of 2 times 1 over square root of 3 plus 1 over square root of 3 and so on and so forth. Now, I can get into the proof of that, but you can see it from book yourself that this series doesn't satisfy that. So in other words, it diverges because if you take limit n reaches to infinity of Cn, it doesn't goes to 0. So it is
Divergent.
by divergence test, you can see that actually this divergence. So you just do these calculations from not that good. Necessarily take loads of time. Okay. That's what 373. 373. So let's move ahead. So what does follows from this result?
Product
Is that if series are convergent,
The product is not.
then product is not necessarily convergent. Okay, so I would like to write without proof. If you are interested, you can see the proof from book. Just making it optional. Something too much. Not everything is less important, but at the moment it's not something of too much of our interest. I'm just writing theorem. You can see proof from book. Okay. Consider life. So suppose. So when this is going to happen, that's what I would like to ask. When this is going to happen? What is the sufficient condition to know that if series are converging, then this should converge? So here is the sufficient condition. Suppose that I have one of the series is absolutely convergent. Converges absolutely, and the second is that again then third property is that A is to B. Then this sum Cn goes to B, where Cn is A from 0 to N, A, K, and B, and okay? So what does this criteria is saying? This this criteria is saying that imagine you want to multiply two series. Okay. So one converges to another converges to B. Then one of the and one of the series is this or this is converging absolutely. So if it is converging absolutely and both series are convergent, then the product will be. Now tell me which thing was missing here?
Absolute convergence
Which absolute?
of this series.
Absolutely.
Converges absolutely.
No, it does not, sir.
Yes. 1 over square root of n plus 1. Why it shouldn't converge?
One about it.
We can go back. I don't see any trouble there. Convergence from that. But one of the key things that was missing is that if I take, for example, an to be A, okay, and bn to be 1 over n plus 1, then this condition is missing. This is missing. Rest is there. Even, okay. Alright. If I choose an to be minus 1 to the n, then this is also missing. Because then you have 1 plus 1 plus 1 plus 1 plus 1. But I have other choice. I can take an to be 1 over square root of n plus 1. And I can choose bn to be minus 1 raised to n. But still in bn this is missing. These two are satisfied for an. But bn is it making sense? So these three are sufficient. So in fact, you have two series. So you need two. So if you want the convergence of product of two series, then both series should converge. First thing, and second thing is that one of them series should converge absolutely. So if this happens, then the product will. Okay. So that's it from series part. There are lots of things, but these were the key things that like to. Okay, we can think of the last thing, which is I'm not getting into details of that, but get that Rudin raised that point that if you rearrange a series, then you can have anything you want actually. Okay. So if I have a series which is divergent, can I rearrange the series? Is it necessary that by rearranging it should converge? So if I have a series which is convergent to some number and I rearrange the same series, is it necessary that the rearrangement is going to converge to the same number? Are it going to converge in first place actually? That no convergence.
Okay.
So this is not the case actually.
Absolute convergence implies convergence. We does not need second property. He does not need a second property.
Oh. Alright.
Sir, but
We can say that, we can make this condition relaxed.
sir, but we can.
Be careful. Here our claim is that this should converge to this specific number actually. And for which you need B. Okay. So if you just want, that's you can reformulate a corollary out of it actually. You can have a corollary. That corollary could be that imagine this series converges absolutely, and this converges, then this is going to converge. That would be. I mean, if you're just interested in convergence,
Then it's
it follows from this. But we want a very specific convergence.
where it is.
That's a good point. It's a very good point. We need this condition because we want that the product of series should converge to API.
Yes, sir.
That's a good point.
without loss of general. Without loss of general.
Okay. So you can take break because I would like to start new task, new topic.
Yeah,